All right. Thank you, Glenn. So I want to start by asking all of you, how many of you have been to at least one of the previous floods talks? Okay, good. Looks like about half of you. This is the part of the presentation where you try to learn who your audience is. Okay, and as usual, you're all over the board. All right. So as Glenn said, this is you're my I don't know. Can I say guinea pigs anymore? You're my test audience for a new presentation that I haven't done before, and so if you all get up and walk out in the middle, I'll know I need to rethink it. But hopefully, you'll enjoy it. What we're doing here is, oh, some time ago, I was watching some science show and the guy said something, and I thought, how do they know that? Sounds really interesting, but how do they know that? So that kind of got me to thinking maybe I might do some kind of a presentation and talk about some of the major flood findings. And in many cases, it's stuff that you've already learned, but maybe you don't know how they figured it out, who figured it out, and when. So I'm taking a little different slant here, but I hope you find it interesting. So I like to compare the figuring out the flood story is sort of like working with a giant jigsaw puzzle. There's hundreds or thousands of pieces, and if you're a puzzle person, you know that you start working on it and you put together some clusters and you can start sort of see what's the picture's going to be, but you got pieces everywhere, and a lot of them you have no idea where they go yet. So what you're going to get tonight, and in fact, what you've been getting from a number of different presentations, is what I call an approximation. And by that I mean that, we're trying to figure out what happened thousands of years ago, or in some cases, hundreds of thousands of years ago, with, in some cases, some pretty sparse evidence. So it's a big challenge. So you're getting an approximation based upon what we know now, but as we learn more, the story will change. So here's what I want you to do tonight. Lean back, relax, not too much, but, relax. And we're going to go through quite a bit of stuff. And I want you to just sort of go with the flow. Don't try to understand everything. And then we'll have a 10-minute break in the middle. Again, I know it's right after dinner and all that. And I recognize glazed eyes when I see them. Okay. So we'll have a 10-minute break. And if you'd hold your questions till the end, that way we can get through the entire presentation. There are so many fun things to talk about. And if we try to do it as we go along, at 8 o'clock or before, Morgan will be kicking us out of here. And I'll say, but, we're still in the middle. So please hold your questions to the end. All right, so how many of you seen this map before? Okay, again, some have, some haven't. This is one of our first products the Ice Age Floods Institute put together, and it is an effort to capture in one map the four Northwest states that were involved with the flood story. Western Montana, North Idaho, eastern Washington, down through the gorge, Willamette Valley, and out into the ocean. So big story, a lot of things happened over long periods of time. So that's what we're going to talk about. How many of you heard of J. Harlan Bretz? All right. Well, we're not going to do the whole floods or Bretz story tonight. We're talking about some other things, but you can't talk about the floods and ignore Bretz, right? So here's a couple of pictures of him. Kind of the couple of key things from 1915 to the 1960s. He was a geology professor at the University of Chicago. Of course, his big claim to fame is all the work he did on the Ice Age floods. But most of that was in the early part of his career, and then he went on and did a lot of other things. He studied uh, caves in a great many states, went to Greenland, studied Glacial Lake Chicago. So a very, very amazing guy in a great many ways. So this is a fun picture I got off the internet a while back. This is Bretz on the left and three of his field assistants. And I like to bring up the point that Bretz was a really very good researcher and field guy, but he didn't do it all by himself. You know, during the 10 years or so that he was out here doing a lot of field work, I think he went through several different rotations of graduate students, and that must have been an amazing experience for them, not only working on the flood story, but to work with J. Harlan Bretz. Okay, so when Bretz and his students first started exploring eastern Washington, they saw some things that looked familiar. For example, you've probably all seen pictures of the rolling Loess Hills, the Palouse, the windblown silt. And that's one of those things that's very common around the world. There's a lot of them in the Midwest. And so when Bretz got out here and started looking at rolling Loess Hills, wasn't anything new to him. He'd seen that before. On the other hand, then he started seeing some stuff that he'd never seen before. And of course, this is the beginning of his work to figure out what happened out here. So, for example, here's a picture of what at one time was a fairly continuous loess cover. And then you can see in the middle there, where the arrow points to, there was something went through there and gouged out all of that loess. You look around a lot of other areas and you see what have come to be known as loess islands. You have a relatively small amount of the windblown silt, but it's surrounded by the other landscapes, the basalt. So, of course, what you're saying is, what happened to all of the loess that used to be there? And in fact, as he looked around more and more, he found areas that not only was all the loess gone, but a lot of the basalt had been eroded away as well. So here you're saying, holy mackerel, what's this all about? And just to, I normally bring this up a little later on, but you got to recall this was like 1920, 100 years ago. And when he was doing this, he did not have satellite imagery. In fact, early on, he didn't even have aerial photographs or continuous topographic map coverage. So a lot of this stuff he's looking at walking on the ground. He and his field assistants walk up one hill, walk down the other, that sort of thing. And there are all kinds of cataracts in the eastern Washington. These big, steep cliffs with what are known as plunge pools below them. Some of those occur in places where there's no water. So, all right, pretty amazing. But what caused that landscape? I'm sure Brett said it much more eloquently, by the way. And he and his graduate students must have had some incredible conversations about this. So one of the other fun things in eastern Washington, of course, most of it is underlain by black basalt rock everywhere. And so you're driving along, and then all of a sudden, you got a humongous big white rock. Where did that come from? Once upon a time, people knew that, okay, glaciers carry stuff like that. The only thing being that glaciers did not get this far south. So where did it come from? There are a lot of these things. Again, 1920s. All right, this is one of the things that I always wondered about was what was it like for Bretz and his field crew working back in the 1920s. And I found this description in Bretz's Flood, which is a book we'll talk about in just a minute. And I thought it was kind of interesting and at least seems to address some of what was involved. I don't know if you can read it or not, but trekking across its expanse on foot with his 3 graduate students, they would camp wherever they happened to be when the sun set at the end of each day. They also made use of a number of railroad lines that crossed the vast and largely empty spaces of the scablands. Disembarking trains, they explored thousands of square miles on foot for days, heading for other train stops whenever they needed to go into one small town or another for food, baths, and a few well-deserved mugs of beer. All right, so part of this is they used the railroad a lot. They hopped a lot of the railroads and went from place to place. Early on, Bretz didn't have a car. Eventually, he got a car. They were able to use that. But the point being that in a relatively short field season each year, Bretz and his 3 graduate students covered a lot of country out there. They looked at a lot of stuff. So then, like you say, for 8 years in the 1920s, they mapped thousands of acres of what he called the channeled scablands. These areas had many large connected channels, which is why they call it channeled, and extensive areas with little or no soil. There was soil there at one time, but something took it away. And I don't want you to tell me yet. I know you know. Okay? All right. So he published 11 scientific papers on this work from 1923 to 1932. He referred to the events that occurred there as the Spokane floods because the floods seemed to come from up here. So Bretz believed that the really unusual landscapes could only have been created by what he called a cataclysmic flood. One of his problems was early on he didn't know where the water came from, and he thought there was only one flood, but he believed the evidence spoke for itself. How you doing? You hanging in there okay? All right. So we're not going to get into the whole Brett's controversy. You've probably heard a lot of that in other presentations, and we're talking about other stuff tonight. But his emphasis on cataclysmic floods really put him at odds with the contemporary geologic thought back in the 1920s. There was a certain school of people who believed that only the processes that they could observe today and the rates that they saw today could be used to explain past events. And so they were not at all receptive to cataclysmic events, especially when he couldn't tell them where the water came from. Okay. So eventually, a lot of new research and new technology helped bring about the acceptance of his ideas. And another important thing was a lot more people came out here to actually see what Brett was talking about. You got to realize after the 20s, the country went into the Depression, World War II. There was a lot of other things going on in the country, and it really slowed down the process of people coming out and looking at what Brett was talking about. So from about the early 30s until 1950, Brett went off and studied other stuff. And his comment was he'd said what he had to say, and other people would either eventually agree with him or whatever. But in the 1950s, when they built the Grand Coulee Dam, and they had all that water behind the dam, and of course, one of the uses of it was to get that water to farmers so they could use them. So then they wound up creating a lot of reservoirs and channels, irrigation ditches all over eastern Washington so that water could get to where the farmers needed it. Well, in the process of creating all these new excavations out there, why, some of the local geologists were going crazy. Look, 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 you know. And so they persuaded Brett to come back out in the 1950s, where he worked on his last major paper that was in 1956. Okay, eventually the tides turned, so to speak, and in 1965 there was a big tour of international experts, and they came out and looked at glacial Lake Missoula, came to the Scablands, and then they sent Brett a long and famous telegram, which ended with, "We are all catastrophists." So Brett's comment, he lived to be 99, and to his dismay, he outlived all of his rivals. And so by the time he was proven to be right, there was nobody around to gloat. And he was very human about all that. Okay, so because we're not spending a lot of time on Brett's, I want to steer you in a couple of other directions. One, there's a book called Brett's Flood by John Sonnington that came out in 2008, and it has a lot of good information on Brett as a person and his family and all that. So if you're interested, that's something to pursue. Another really good book, Cataclysms on the Columbia, that came out in 2009. This has some good discussions about the controversy between Brett's and all the other prominent geologists of the time. And so you can go there and see what they all were arguing about. The other thing that's really good in this book is it touches on a lot of the newer researchers that came along that have been building on Brett's work. And you can learn about them from that book as well. Both available from the Institute store. How many of you are members, by the way? All right. Hopefully you will leave here energized and ready to become members. Okay? You see, I see people are still. All right. We got to joke a little bit. It's right after dinner again. All right. So here's a famous quote by Sir Isaac Newton. If I have seen further than others, it is by standing on the shoulders of giants. By that, he meant that he was able to do a lot because he was able to build on the work of the people who had come before him. So in our case, we're standing on the shoulders of a giant, J. Harlan Brett's. And ever since 1956, people have been building on his work. And fortunately, this is one of those things, one of the reasons it's so fascinating for all of us is that they haven't got it all figured out. We all like a mystery, right? And we haven't got to the last chapter. We don't know who did it yet, but okay. All right. So all of that stuff's kind of lead in, intro, background. So these are the things that we're going to talk about here in the last part of the presentation. Some questions that I thought would be fun for us to discuss. So the first one, how do we know there was a huge glacial lake in western Montana? How do we know it drained rapidly? About when did the floods occur? About how many floods were there? Where did the floodwater come from? And then how long did it take the floodwater to move through the various pathways and eventually reach the Pacific Ocean? So that's what we're going to spend a little time on. Okay? I'd like to pause and ask you to... All right, good. So question one, how do we know there was a huge glacial lake in western Montana? Question 1A, who first figured it out and when? Well, most of you, if you've seen been to very many flood stalks, somewhere in there, there's a picture like this of all of these ancient shorelines in the Missoula area, right? How many of you have seen that before? All right, good. All right, so then the question was, who first recognized that that's what he was looking at, glacial lake shorelines? Well, come to find out, it was a geologist by the name of T.C. Chamberlain, kind of a famous guy, who was traveling through western Montana in 1886. So one of the things that I thought was really interesting here is that some of these things are not new discoveries, but we've known about them for quite a while. And your trivia is, towards the end of his career, Chamberlain was at the University of Chicago, where later on J. Harlan Brett's was. Fortunately or unfortunately, their paths didn't cross, I don't think. Okay, another early paper which was important to learn about. This is Joseph Pardee, and some of you have heard of him before. But he wrote a paper in 1910, and as far as we know, this is the first published article on glacial Lake Missoula in the Journal of Geology. And the purpose of the paper was to show that in comparatively recent time, an ice dam lake filled a large part of the drainage basin of the Clark Fork River in northwestern Montana. And Pardee described those ancient shorelines up to 4,200 feet in elevation. He gave Chamberlain credit for the discovery, as well as his tentative suggestion that the ice dam was in Pend Oreille area of Idaho with outflow by way of Spokane. 1910, they were talking about some of this and kind of had, a lot of times people think until J. Harlan Bretz came along, nobody knew anything. Well, no, that's not exactly true. And so Joseph Pardee, 1910. So one of the interesting things, I don't know if you've done this or not, but with a lot of floods features, if somebody points them out to you once in one area, so you know what you're looking at, then as you drive around, you start seeing other places that have that very same thing. And so, for example, as you go from Missoula to other areas, this is the Bison Range in western Montana. The arrows pointing to some more of those parallel ancient shorelines. Can you see those? Some people say they're kind of like bathtub rings, They go all over western Montana at about that same level. An interesting thing, this was a photo by Roy Breckenridge, who was the Idaho state geologist for years and years. There was a forest fire up there in the Clark Fork area, which is, the north end of Lake Pend Oreille. And lo and behold, without the trees, you could see what was there. It was those ancient shorelines going from Missoula all the way around western Montana, right up to where the ice dam was. So when you're driving around western Montana, look for things like this. And here's another thing you can look for. Most glacial lakes leave deposits that look like this. They're not river gravels, they're not sand and big boulders, that kind of thing, but they're layers of very fine sediment. Those are glacial lake deposits. And as you drive from here to Missoula, for example, and other areas in western Montana, you can see these places where the highway goes through them or the river cuts through them. So just more evidence that at one time there was a big glacial lake in there. All right, we're done with question 1. And I don't see any head bobbing yet. That's encouraging. All right, question 2. How do we know glacial Lake Missoula, which held up to 520 cubic miles of water at maximum depth, drained rapidly? And question 2A, who first figured it out? Well, the first evidence is from a place called Camas Prairie, Markle Pass, which is southwest of Flathead Lake in western Montana. And here's Joseph Pardee again, guy we talked about just a couple minutes ago. Well, he presented a very famous paper at a meeting in 1940 on ripple marks, question mark, in glacial Lake Missoula in Montana. And then he published a journal article a couple years later. So what Pardee discovered, that we'll talk to about in just a minute, he would not have been able to discover except he was able to get some aerial photographs from the Forest Service. And I like to say that in studying the Ice Age floods, there is no substitute for the big picture. You know, if you're down here wandering around on the ground, there's a lot of things you can't figure out. He found giant current ripples, which he believed were formed by deep, fast-moving water. This is a wonderful photograph by Bruce Bjornstad. And to put it into perspective, that's the farmhouse. Okay? So these giant current ripples are truly giant current ripples. So people had walked over these features without knowing what they were. The ripples were 13 to 50 feet high, 200 to 500 feet apart, and the white arrow shows the direction of the water movement. All right, here's another even bigger picture. And the arrows point to all of the different giant current fields there. Can you see those? All of this kind of stuff. Pardee said that those ripples were formed by 800 feet deep water moving over 60 miles an hour. And he had found the source of Bretz's flood. Although the other part of the story is Bretz didn't listen to him. But that's subject for another. So Vic Baker, who's a very prominent floods researcher, identified 60 major areas of giant current ripples throughout the Channel Scablands. So in other words, those amazing ripple marks were not just found in one or two places, but he found 60 major areas and something like 100 total sites. So what that told people was that that fast-moving deep water had covered most of the Channel Scablands in reality repeatedly. And this, the presence of all of these giant current ripples, was one of the major pieces of evidence that convinced the researchers that maybe Bretz was onto something. So question 3, when did the Ice Age floods occur, and how do we know that? And just in general, this is a good place for a definition of the Ice Age. It's a general period of time between about 2.6 million years ago and about 14,000 years ago. Numerous cycles of glacial advance and retreat. And for purposes of studying the floods, it's important to know that there's a lot of evidence of the most recent floods. But when you try to look at some of the earlier floods, there's less and less good evidence. There's enough that we know that the most recent ones were not it, that over the last 2 million years, we've had a lot of glacial activity, a lot of flooding. Okay, so go back to the question, how do we know when they occurred? So the methodology used for dating depends on the age of the deposit. So how do researchers determine the approximate age of younger flood deposits. Now, you'll notice all through my presentation, I use lots of abouts and approximately's and those kind of what I call weasel words, because fact is, a lot of these things, we know about when they happened, but it's not an absolute. So if you're going to date the younger flood deposits, you have to get really lucky and find something you can date, principally either organic materials or volcanic ash. And of course, it probably doesn't come to any surprise to you, but when you've had all these floods going everywhere over thousands of years, eroding stuff, burying stuff, that going out there and trying to find organic material probably is not an easy thing to do. But a very small amount of organic materials, wood, bone, seeds, mammoth tusks, shells, and peat, have been found in the floods area. These have been used to date the layers they are found in using carbon-14 dating, which can date materials back to, I think now, about 60,000 years ago. The other thing that's very useful is volcanic ash. You all know about all the Cascade volcanoes, and at one time or another, they've erupted, blown ash into the air, and because the prevailing wind is from the west or southwest, some of these materials are sometimes found in the floods area. And each of those ash falls has been studied intently. And so when researchers find an ash layer, they can send it to the lab and get confirmation of which volcano it came from and when. So this is just a nice little graphic I found that shows all of the Cascade volcanoes. And there's two volcanoes in the Washington Cascades that are very important in flood age determination. That's Mount St. Helens and Glacier Peak. And the way the two ash layers are used, and this is an example, this is a photo from Nick Sintner showing the white layers are Mount St. Helens S ash, which is about 16,000 years before present. And this layer tends to be found kind of in the middle of all of the flood deposits. So there's some deposits below that and some on top of it. It's an incredibly important layer. Glacier Peak, when you find that, that's 11,600 years before present. And when that showed up, the flooding was basically done. So you find it, that tells you that, anything flood related is below that. But the important one is the Mount St. Helens S. So based on the dates that have been obtained from organic material and the two ash layers, the younger floods are commonly estimated to have occurred between 18,000 and 15,000 years ago. So when we talk about the recent floods, that's the period of time we're talking about. Started about 18,000 years ago, ended about 15,000 years ago. So something like in a 3,000 year period of time. I have to share with you that when you get into the literature, there are more numbers than you would ever want to see. And they rarely agree, you know, and there's reasons for all that. But again, so we say about between 18,000, 15,000. That's what that means, is about that general time period. Okay, now we're going to look a little bit at the floods that were much older than that, older than 18,000 years ago. And again, because the evidence is not near as abundant, we know not near as much about them. We don't know for sure where the floods came from way back then, how many there were, a lot of that kind of stuff. A review of the literature in 2012 documented 25, 25 scabland areas having flood deposits older than the Missoula floods. Okay. Okay. I like to pause periodically. And if nothing else, you say, oh my God, he stopped. What's going on? All right. Okay. So those older flood deposits, the one that are back there older than the Missoula floods, how do they identify them? Well, there's a number of ways, some of which I think I understand, and there's some I clearly don't understand, and I'm smart enough not to try to explain to you something that I don't understand myself. So we're going to talk about the two ways that make the most sense to me. Okay, the older flood deposits, then, the first way uses paleosols, which is just a fancy word for old soils, very old soils, older, highly weathered soils that frequently contain thick, very hard, white layers called caliche. Takes thousands of years for these thick calcium carbonate rich layers to form, usually in a dry climate. The nice thing about caliche is you and I, if we're driving through the scablands and you're looking at road cuts, which is addictive after a while, why, you will sometimes see a white layer like that, and you stop, pull over safely, and go and look at the layer, and it's white and it's really hard, and a lot of times fairly thick, then more than likely that's caliche. That's one of those very old deposits. If you really get into this, you could carry a little bottle of hydrochloric acid, and if you put a couple of drops of hydrochloric acid on the caliche, it just effervesces, bubbles, because you're given the carbon dioxide is given off, and that's a way you can confirm that white hard layer is calcium carbonate. All right, but at any rate, to me, the neat thing about it is some of the other stuff we talk about. I wouldn't know how to look for it when I was out there, but when you're driving through the scablands and you look for a good, solid white layer in a road cut, you may be onto something. Okay, I like to get this to something that you and I can see and can figure out. Okay, so the second way of dating older flood deposits is related to the Earth's magnetic field. And of course, it's been used for centuries for navigation. You got the geographic North Pole, you have the magnetic pole, and the magnetic pole kind of wanders around up there. And periodically, like every 780,000 years or so, they do a reversal. So as a practical example, how many of you have you ever used a map and a compass? Okay, good. So that's just a confirmation that this magnetic field business really is true. So with paleomagnetism, what are we talking about? Well, when some rocks and sediments, if they contain magnetic minerals like magnetite, when they solidify, the magnetic mineral will solidify with the orientation at whatever the north pole was, the north magnetic pole was at that point in time. So it freezes that feature in the rock. So then, and then, like I say, the thing about the poles, and we'll look at an example in a minute. Sometimes you have a exposure and it's normal polarity, and then you reach a point where it's reverse polarity. The stuff below it having shifted during the pole reversal and telling you that it's older than 780,000 years. Okay, so here's kind of an example. This is a nice photograph from Bruce Bjornstad, who some of you know. And the idea being that those rolling Palouse hills, that loss that we talked about early on, when the researchers started looking at those, they found that it was not just the same stuff for 200 feet, but when they started looking at it, they found in many cases there were layers of buried soils down there. And so the idea being you had some loss blew in, accumulated, and then the landscape was stable for a pretty long period of time. The soils formed, the bunch of weathering went on, that calcium carbonate, that caliche leached out, and then got some more windblown loss coming in. That happened numerous times. And so when you find an exposure like this one in Bruce's picture, you can see that there towards the top, you walk over there, the stuff above this is normal polarity. The stuff below this is reverse polarity, telling you that this stuff is older than 780,000 years. And also, of course, what you can see there, great illustration of Bruce's, is you see those periodic white layers. That's the caliche. It's the calcium carbonate stuff. So then basically all we want you to get out of this is that this is the kind of evidence that's used to when people say, well, there weren't just more recent floods, but there were floods that happened back perhaps 1,000,000 years ago, maybe 2,000,000 years ago, a long time ago. All right, that's a good place to pause for a minute. Are you doing okay? All right, that's some of the more complex stuff. Okay, so question 4 is a biggie that's been around a long time about how many floods were there. And when Brett's first started, he said there was one really big flood, and that was pretty tough for a lot of people to swallow, because when he tried to point out all the things that had happened, and he was saying it all happened with one flood. Boy, that's tough to comprehend. So eventually, then Brett's said, well, perhaps there were 6 or 7. And researchers have been working since then, continuing to try to figure out how many floods there were. Still work in progress. So this is you might say, wait a minute, that's the Grand Canyon. Did he put the wrong slide in? No, this is there for a particular reason. And mainly to, how many of you have been to the Grand Canyon? All right, marvelous exposure. My wife and I, a number of years ago, we took the mule ride down to the bottom of the Grand Canyon and stayed at Phantom Ranch and came back the next day. But it's wonderful because you're going down with the mule and the rock is right there. And the drop-off is... and you're thinking, boy, I hope this mule knows what he's doing. But I put this in there because it's unusual geologically to have a place where so much history is exposed in one place. I mean, you have all these rock formations. The one at the top is the youngest, and they go progressively down to the oldest. And unfortunately, when you're studying the floods or most other geologic events, you don't have this kind of a luxury. What you're dealing with is more scattered partial exposures over huge areas, and the geologist has to try and look at those things in 3-dimension and figure out what happened, what's the big picture. So the other reason then for saying this is when the geologists are struggling to figure out how many floods there were, one of the problems is you don't have this kind of exposures. So there's 2 USGS researchers, Brian Atwater and Richard Waite, are the ones who have done a lot of work in Central Washington, and their thinking is that, Brian Atwater, he thought there were something like 89 floods. Richard Waite thought probably 95 or perhaps even more than 100. And so thought I would kind of show you what they use what makes them think that, okay? So this is a very famous place called Burlingame Canyon over in the Walla Walla Valley. One of the things that makes it really unusual was it wasn't there until like 1926, and they had an irrigation ditch that ruptured, and all this water got concentrated into a new area that was very erodible, and it created this deep exposure of all of these really neat layers. And so this is the place where Richard Waite put together a lot of his ideas about how many floods there were. And each of these individual beds that the yellow arrow points to, called rhythmites, each one of those areas is coarse at the bottom and then gets finer as you go to the top. And these are kind of slackwater deposits. So the idea being the flood went pouring through the main area. Some of this water gets pushed up into the side drainages where it's kind of protected, and then things settle out. And this way, the next flood doesn't erode it, but it's still there. And in this case, Richard counted 40 of these graded beds. And so the question was, is each one of those beds represent a separate flood, or are some of them perhaps the result of one flood, dropping several beds in there? And so fortunately, when Richard started looking at that very carefully, one of the things he found, and I can't really point to it because I don't know exactly where they started counting from the top, but they found a layer of the Mount St. Helens ash, S, 16,000 years ago. So that told him then that all of the beds below that were older than 16,000 years. The ones on top were younger. Now, the other thing, when he started looking at those very carefully, he noticed that in some cases, at the top of the bed, there was a bunch of biological activity. In other words, that area had been free of water for a long period of time. Soil started forming. Critters were in there doing things, creating burrows and all of that. And so he found enough evidence of that scattered around there at the different beds to lead him to believe that each one of those represented a separate flood. Okay, I know that was a little tedious. I could see people's eyes glazing over a little bit. Okay, next question. We have question 5 and question 6. The ending is in sight, friends and neighbors. All right, so question 5, where did the floodwater come from? So I break that into what are the known water sources, and then raise the question, are there unknown water sources? Well, so the known water sources, of course, you know about Glacial Lake, Missoula, and we haven't really talked about it, but perhaps at other talks you've learned about Glacial Lake Columbia, and it was formed when the Okanagan lobe came down and dammed the Columbia River. And so most of the floods came from Glacial Lake, Missoula. Um, a lot of them flowed into Glacial Lake Columbia after it formed, and then out of there and to the south. So those are known. Richard Waite, that we talked about a few minutes ago, in some of his publications, he also identified Glacial Lake Kootenai in British Columbia. It was a source of floodwater as the ice lobe there that was in the Purcell Trench in Idaho, as that retreated, it dammed some other drainages and caused some floodwater to go out of there, flow like the Blue Arrow into the Columbia River and into our area. Not a major source, I think, but a source. And we don't talk much about this, but I wanted to at least put one slide in here. Of course, one of the other major floods was Lake Bonneville. And, that's the one, the ancestral Great Salt Lake, broke through a Red Rock Pass there in southeast Idaho, came down the Snake River, Hells Canyon, ultimately into the Columbia, and then out into the Pacific Ocean. Really big flood, but there was only once, and it was spread over a longer period of time, and it didn't go through the scablands, so it's not a major factor there. So the researchers have been wondering ever since they started all of this, they wonder whether glacial Lake Missoula, again, which had 520 cubic miles of water when it was at maximum filling, was it big enough to cause everything that happened out there? And they've gone back and forth. For a while, they said, no, not enough. And then another generation came along. They said, yeah, we think it's big enough that could have done all that. Well, one of the problems they're having more recently, they're doing a lot of modeling. And we'll talk a little bit more about this. But when you do a model, you're trying to simulate past events. And one of the things that helps the modeling is that people have been mapping the floods for 100 years. So they know where the water went. They don't know how much and when and a lot of those things. But there's some good fixed points out there on the landscape that they can use to validate their models. And the problem that they're having now is they haven't been able to come up with a model that hits all of those high water marks. So their conclusion is they're perhaps missing another water source. So just an example, I haven't got it all figured out yet. Okay, question 6. This is an easier one. People have often wondered how long did it take when the ice dam failed and glacial Lake Missoula started draining? How long did it take all of that water to get through all of these brown areas, which represent the areas of major sediment removal by the floods? So how long did it take all that to happen? So the modeler's been working on that. So before we look at their conclusions and the end of my presentation, I know when you say end, people perk up. All right. Okay. Here's a few things to be aware of. With the 100 floods, however many there were, they weren't all really big. Okay. Some floods were much bigger than others. Perhaps 40 or so of the most recent floods made it to the ocean. They have found evidence in the Willamette Valley of deposits from 40 floods. So the thinking is that a lot of the other smaller floods were not big enough to make it all the way there. Okay. So we're talking about maybe 40 of them made it. Large amounts of flood sediment is found in the ocean. Some of the research that's been done off the coast, where they have looked at all of that sediment that washed down all the way down the Columbia, went out into the ocean. Some of it went down to Northern California. A lot of water, a lot of sediment. But the difficult thing is all of that stuff in the ocean is incredibly difficult to sample and to measure. So that's our answers, but costly. Okay, so some of the modeling considerations. So modeling is used to simulate what happened. Field evidence from the actual mapping is used to calibrate the model and judge accuracy of the simulations. And this is a bunch of background stuff that you won't remember, but so you can kind of see what's involved. So if you're going to model something, it's really important to decide what conditions are you modeling. And again, no two floods were probably the same. This particular simulation used a large, but not the largest flood, and assumed the Okanagan lobe had came down and blocked off the big bend of the Columbia River. Here's an interesting thing, and I know it's improved since then, but the reality is back then, this computer run took from 250, I read it the other day, to 500 days of computer time. That's how complex the analysis is for such a big area. Okay, so what did that simulation tell us? Well, the results were that they think glacial Lake Missoula drained in about 2 days. And that assumes that the ice dam had to have failed pretty big. You got to open up a really big hole to let 520 cubic miles of water get out of there. So about 2 days. On its way out through there, the arrow points to the Cheney-Palouse Scabland tract, and as the water from glacial Lake Missoula got there, it filled that area in about 24 hours, and in about 55 hours, all the water had drained out of there and to the south and west. The Pasco Basin filled in about 38 hours and began to drain in about 55. Okay, in about 3 weeks is the estimate for how long it took all of the water to get through the Columbia Gorge and out to the ocean. And you can see why the gorge is the bottleneck. That's a really narrow area. And so a lot of water backed up into Lake Lewis and all of that. All right. The last slide. Hallelujah, right?